Hi everybody, in this video I'm going to talk about binomial random variable. Binomial random variable is an extension of Bernoulli random variable. For instance, if you toss a coin once, the possible outcomes is either getting a head or a tail. So you have only two possible outcomes, and it's an example of Bernoulli random variable. But now if you keep tossing this coin n number of times and then observe the number of heads and consider that getting ahead is a success, then we have a special name for this kind of distribution in probability theory, and we call it binomial. Binomial distribution basically arises from counting successes. Suppose an experiment consists of n independent Bernoulli trials. Let X denotes the number of success in n independent trials. And yi denotes the outcome of trial I. And remember, all these trials are Bernoulli trials. So we have only two possible outcomes, either a success or a failures. And we assign value 1 if the ith trial is success, and if we assign value 0 if the ith trial is failure. X denotes the number of success. So X can be written as sum of all the yi's from 1 to n. So binomial random variable is basically conducting a Bernoulli random variable, conducting a Bernoulli experiment n number of times and observing the success obtained in those n trials. A random variable X is said to be binomial random variable with parameters n and p if X is number of the success in n independent Bernoulli trials. The probability of success in each trial is p. Example, a fair coin is flipped 20 times. X represents the number of heads. So what do we have here? We know that a fair coin is being flipped and we will either get a head or a tail. So it is a Bernoulli trial and we are conducting this Bernoulli experiment 20 number of times. Therefore, n is equals to 20 and the X represents the number of heads. The probability of getting a head is equals to 1 by 2 when you toss a fair coin. Therefore, it is an example of binomial random variable, and the value of the parameters n and p is 20 and 0.5 respectively. Roll a fair die 50 times. And X represents the number of times you get a 6. It is again an example of binomial random variable, because here when you roll a die once and you notice that success represents getting a 6, it is a Bernoulli trial. When you are conducting it 50 times, it becomes a binomial random variable with n equals to 50, and the probability with which you get a 6 would be 1 by 6, because when you roll a die, the probability of getting 1, 2, 3, 4, 5, 6, any outcome is equals to 1 by 6. It's an equally likely outcome. Therefore, the probability here would be 1 by 6. Consider tossing a coin repeatedly, and X denotes the number of times you get a head. Now, if you toss a coin once, and X represents the head, which means that head is a success, then in that case, we will have that it is a Bernoulli trial. But here we are tossing a coin repeatedly and does not have any fixed number. Therefore, it is not an example of binomial random variable, because the probability is half, because we are tossing a coin and X represents the head. So P is equals to 1 by 2, because probability of getting a head and probability of getting a tail is 1 by 2, but the value of n is not fixed. You are just tossing a coin repeatedly. You might just toss it forever. Therefore, X is not binomial random variable because the number of trials is not fixed. Okay, let us calculate the probability mass function of this random variable X. An important thing to note is that the support of this random variable is 0, 1, 2, all the natural numbers starting from 0 to n. Let's say you conduct an experiment n number of times, and X represents the number of success, the number of times you get a success when you conduct this experiment n times. So it is very much possible that when you conduct this experiment first time, you might get a success. When you conduct it the second time, you might get a success again. When you conduct it third time, you might get a success again, and you might get success at each and every trial. So you have n number of success because you have a success at each trial. Therefore, in that case, x can take value n. Also, it is possible that every time you conduct the experiment, you might just get a failure. In that case, the number of success in n trials would be equals to 0, and x can take value 0. Another case would be that when you conduct the experiment first time, you might get a success, and if you conduct the experiment after that, you might get a failure each and every time. Therefore, in that case, x can take value 1, and thus the support of x over here can take any value between 0 to n when you are conducting the experiment n number of times. Time to write the PMF of this random variable. So the probability mass function of a binomial random variable describes the probability of obtaining exactly k successes in n independent Bernoulli trials, where each trial has the same probability p of success. So now we are selecting k success out of n trials. And how can you do it? So here NCK represent the number of ways to choose k success from n trials. P to the power k represents the probability of k success, and 1 minus p denotes the probability of n minus k failures. Therefore, the probability would be equals to NCK, that is the number of ways to choose k success from n trials, times p to the power k because you obtain k success in n trials, times 1 minus p to the power n minus k because if you have k number of success, then you have n minus k number of failures, and probability of getting a failure is 1 minus p, and thus you have 1 minus p to the power n minus k. And therefore, probability mass function over here, which gives the probability of obtaining exactly k success in n trials, considering all possible ways this can occur, is equals to nck times p to the power k times 1 minus p to the power n minus k, where k can take value 0, 1, 2, 3 till n. The next thing is to prove that this PMF is valid. Now, whenever we have to prove that a PMF is valid, we need to prove that it is non-negative. And clearly here, the PMF is non-negative because the value of pxk is nck times p to the power k times 1 minus p to the power n minus k. Now, p represents the probability of success, and we know that probability is always between 0 and 1. 1 minus p represents the probability of failure, and since p is between 0 and 1, 1 minus p will also be between 0 and 1. And n is strictly greater than 0, k can take any value between 0 to n, therefore nck is positive, and we can say that this pxk is non-negative for all values of k between 0 to n. Okay, the second property which we will have to prove to say that it is a valid PMF is that sum of this PMF over the support equals 1. And to prove this, we will use the binomial identity, and the binomial identity is that sum of a plus b whole to the power n is equals to summation k from 0 to n nck a to the power k times b to the power n minus k. Now, this binomial identity is very important because we can straightforwardly apply this identity and we will be able to prove our second condition. So let's consider from k0 to n, and then we have to find the summation of pxk of this PMF. And what is the value of PMF? It is nck times p to the power k times 1 minus p to the power n minus k. Treat a as p. Use this binomial identity, you treat this a as p, treat this b as 1 minus p. So if you treat this a as p, b as 1 minus p, then this part will become equals to a plus b to the power n. Now you're treating a as p, b as 1 minus p. So you get that this expression is equals to p plus 1 minus p whole to the power n. And if you simplify it, p and minus p will cancel out and you will get 1 to the power n, which is just equals to 1. And this PMF satisfies both the condition and we can say that it is a valid PMF. Perfect. It's time to find the cumulative distribution function. Let's say that k is a positive integer. Again, here we are considering that k is a positive integer. If k is a positive integer, then CDF of at k would be equals to probability of x less than equals to k. And if you use this formula, like if you find probability x less than equals to k, it basically means summation t from 0 to k, nct, p to the power t times 1 minus p to the whole power n minus t. Now, we cannot really simplify it further. So whenever it comes to cumulative distribution function of binomial random variable, we just leave it over here. Time to find the expectation of this random variable. Now we know the formula of expectation of random variable is summation of kpxk, where we are summing over the support of the random variable. Here the support of the random variable contains all the natural number between 0 to n. So we have summation k from 0 to n of kpxk. We know the value of pxk, which is nck times p to the power k times 1 minus p to the power n minus k. We can clearly see that at point k equals to 0. So we are summing at k equals to 1, k equals to 0, k equals to 2, k equals to 3 till k equals to n. And we know that at k equals to 0, this expression, the value of this expression is equals to 0. So the value of the sum is basically same as summation when the sum starts from 1 to n, because at k equals to 0, the expression has value 0. We can further write this nck as n factorial divided by k factorial times n minus k factorial. And we get the last inequality. Furthermore, we can write n factorial as n times n minus 1 factorial. And in the numerator where we have k factorial, it can be written as k times k minus 1 factorial times n minus k factorial. And all the other terms we have as it is, that is p to the power k times 1 minus p to the power n minus k. Now, if you carefully notice, we have k in the numerator, we have k in the denominator, we can cancel it out, and we will have expectation of x is equals to summation k going from 1 to n times n minus 1 factorial divided by k minus 1 factorial times n minus k factorial, p to the power k times 1 minus p to the power n minus k. So we are basically adding and subtracting 1 in this term n minus k. So wherever you see n minus k, you just add and subtract 1, and then you pair it as n minus 1, and you write k minus 1, you pair k minus 1 together. So this n minus 1 plus 1 minus k will become n minus 1 minus k minus 1. Wherever you see n minus k, you just write it as n minus 1 minus k minus 1. If you do that and pull out this n sign out of the summation sign because it does not have any term of k, so there is no point writing n inside the summation sign, we can just pull it out. This is the expression we will have. So what do we have? We have summation k going from 1 to n minus 1 factorial divided by k minus 1 factorial. And now we have written n minus k factorial as n minus 1 minus k minus 1 factorial. Again, repeating, we have this negative, we are doing it by, we get it by adding and subtracting 1. And then we have p to the power k. Now, since we have made this n minus k as n minus 1 k minus 1, we will make this k also here also to the power of p. We will add and subtract 1, and we will get p to the power k minus 1 plus 1 times 1 minus p to the power n minus 1 minus k minus 1. Now, why did we add and subtract 1? Because in the denominator, we have k minus 1 factorial. So everywhere we saw k, we just modified, we just added something, subtracted something to make the k everywhere, to modify and change this k to k minus 1. Okay, so perfect. So we have n minus 1 factorial in the numerator, and in the denominator we have k minus 1 factorial times n minus 1 minus k minus 1 factorial times this term. Now, if you carefully see, this p to the power k minus 1 plus 1 can be written as p to the power k minus 1 times p. And that p can be pulled out of the summation sign. Why can we pull out this p out of the summation sign? Because it does not involve any term of k, and the summation is over k, where k varies from 1 to n. So we can just pull it out, and this is what we have now. Okay, now if you carefully see, we have n minus 1 factorial divided by k minus 1 factorial times n minus 1 minus k minus 1 factorial. And if you carefully see, this is nothing but n minus 1 choose k minus 1. If you write it in the compact form, it is just n minus 1 ck minus 1. So we write this expression as n minus 1 ck minus 1, and we will get the last inequality. So now take k minus 1 is equals to x. So wherever you see k minus 1, you just replace it by x. So p to the power k minus 1 will become p to the power x. 1 minus p to the power n minus 1 minus k minus 1 will become n minus 1 minus x. N minus 1 ck minus will become n minus 1 cx. And now, most important thing, here the sum starts from k equals to 1 to n. Now, we are taking k minus 1 is equals to x. So now the series, we will have the summation over the values of x. Now, since we are taking k minus 1 is equals to x, therefore, the lower limit of x will become 0, because the lower limit of k is 1. And if you put k equals to 1 here, the lower limit of x would be 1 minus 1, that is equals to 0. And the upper limit of x would become n minus 1, because the upper limit of k is equals to n, and you are taking x is equals to k minus 1. So if you take this, put this k is equals to n, you will get the upper limit of x, which is n minus 1. Okay, so expectation of x is np summation x from 0 to n minus 1. N minus 1 cx p to the power x times 1 minus p to the power n minus 1 minus x. Time to use the binomial identity. So this binomial identity is very important. We use it every time. We use it to prove valid PMF. We use it to find expectation. And you will soon see that we are going to use it when we find variance. Okay, so now if you look at the binomial identity, it says that a plus b whole to the power n is equals to summation k going from 0 to n and ck times a to the power k times b to the power n minus k. Now, if you look at the inequality, if you look at the expression above, treat x as k, treat p as a, treat 1 minus p as b. So if you treat x as k, treat p as a, and treat 1 minus p as b, you will have that this expression is equals to np times a, you are treating as p, so you will have p plus 1 minus p, because you are treating b as 1 minus p, whole to the power. Now you see here in binomial identity, you have summation k from 0 to n minus n. Therefore, you have a plus b to the power n. Here, in the expression of expectation of x, we have summation of x from 0 to n minus 1. Therefore, now, in our case, we will have expectation of x to be np times p plus 1 minus p whole to the power n minus 1. Again, why is it n minus 1? Because here we are summing from 0 to n minus 1. Okay, now inside the bracket we have p plus 1 minus p and p can cancel out, and we will be left with 1 to the power n minus 1 to the power n minus 1, which is just 1, and therefore we have expectation of x is equals to np. Okay, so we know that if we have n number of trials, n number of Bernoulli trials, and p represents the number of success, then the expectation of a binomial random variable is number of trials times the probability of getting a success. time to find the value of variance. So variance of x is equals to e to the power x square minus e to the power x whole square. We already have the value of expectation of x. So we just need to find expectation of x square. So we will write e of x square is equals to expectation of x square, and we will add and subtract x over there. So we will have expectation of x square minus x plus x. Now treat x square minus x as one random variable and x as another random variable. And then if you use the property of linearity of expectation, you will get that this is equals to expectation of x square minus x plus expectation of x. Now, this x square minus x, if you factor out x from here, you will get expectation of x times x minus 1. We already know the value of expectation of x. So now the goal is to find expectation of x times x minus 1. Now, you can directly even start finding the value of expectation of x square by using the formula summation k square times pxk, where you are taking the summation over the support of x. But again, there also we use this sort of modification. So why not to make this modification in the start and just find the value of expectation of x times x minus 1 in the start, and then add it to the expectation of x in order to get the value of expectation of x square. Now remember, we will use this modification in finding the variance of most of the other discrete random variable. Okay, so now the goal is to find the expectation of x times x minus 1. So what is expectation of x times x minus 1? Here we will use the formula that whenever we have x as a random variable and whenever we have to find the expectation of a function of x, it is equals to summation function of x times the probability mass function of x. So therefore this becomes summation k times k minus 1 times the probability mass function of the random variable x. Okay, now we are taking the summation over the support of x. The support of x contains all natural numbers from 0 to n, therefore we are summing it from 0 to n. Perfect. Now if you carefully notice, at k equals to 0, summation k equals to 0 to n means that you are finding the sum of this expression when k is equals to 0 plus k equals to 1 plus k equals to 2 plus k equals to 3, so on and so forth till k equals to n. And if you carefully notice, this expression has value 0 when you take k equals to 0 because you have a factor of k over here. When you take k equals to 1, this expression will again be equals to 0 because you have a factor of k minus 1. Therefore, this expression is same as summation k equals to 0 to n of this expression is same as summation k going from 2 to n of that expression. Okay, there's one more change which you're going to make. Write k factorial as k times k minus 1 times k minus 2 factorial, and write n factorial as n times n minus 1 times n minus 2 factorial. So we are doing two things at the same time. The first thing is we will write the summation k going from 0 to n. We will just change it to k equals to 2 to n because at k equals to 0 and k equals to 1, the value of this expression is just 0. Also, we will just write k factorial as k times k minus 1 times k minus 2 factorial, and n factorial as n times n minus 1 times n minus 2 factorial. Perfect. If we do that, this is what we're going to get. Now, if you carefully see, you have k times k minus 1 in the numerator, you have k times k minus 1 in the denominator. You cancel it out. And next thing you see is that this n and n minus 1 does not have any term of k related to it. So you can just pull it out of the summation sign and you will have n times n minus 1 times summation k going from 2 to n of this expression. Awesome. Now, in this expression, you will notice that we have k minus 2 factorial in the denominator. So in this case, we will add and subtract 2 like wherever we see k, we will just add and subtract 2 over there. Okay, while we were doing it for expectation, we had k minus 1 factorial over there. So we added and subtracted 1 wherever we saw k. Now what are we doing? We have n minus k. So we will just add and subtract 2, and we will write it as n minus 2 minus k minus 2. Perfect. And I said wherever we see k, we just add and subtract 2. So we already had n minus 2 factorial in the numerator, k minus 2 factorial in the denominator. In the denominator, we had n minus k, so we will just write it as n minus 2 minus k minus 2 factorial. And we just had p to the power k in the numerator. Now we will add and subtract 2. So we will have p to the power k minus 2 plus 2. And then we will have 1 minus p to the power n minus 2 minus k minus 2. So we just had n minus k over there. So here we will have n minus 2 minus k minus 2. Perfect. Now, this n minus 2 factorial divided by k minus 2 factorial times n minus 2 minus k minus 2 whole factorial can be written as n minus 2 c k minus 2. So this is the compact form of this expression is just n minus 1 c k minus 2. Perfect. Now take k minus 2 is equals to x. If you take k minus 2 is equals to x, this expression will become summation n minus 2 cx p to the power x 1 minus p to the power n minus 2 minus x. Okay, now carefully look at the summation sign. So this summation sign in the above inequality, here we had k going from 2 to n. Now we are taking k minus 2 is equals to x. Therefore, we will have to change the limits to the limit of x. The limit of k will change to the limit of x. Now, what will be the lower limit of x? X is equals to k minus 2. So the lower limit of x would be lower limit of k minus 2. Lower limit of k is 2. Therefore, the lower limit of x is 2 minus 2, 0. The upper limit of x would be equals to the upper limit of k minus 2. The upper limit of k is n. Therefore, the upper limit of x would be n minus 2. Therefore, the summation would go from 0 to n minus 2. Okay. Again, we will use the binomial identity. What does binomial identity say is that summation k going from 0 to n nck times a to the power k times b to the power n minus k is equals to a plus b whole to the power n. Treat a as p, b as 1 minus p, k as x. And here, now we have n minus 2 instead n. Therefore, the sum will become p plus 1 minus p whole to the power n minus 2. P and p will cancel out, and you will have expectation of x times x minus 1 is n times n minus 1 p square times 1, because p and p cancel out, and you'll be left with 1. 1 to the power n minus 2 is just 1. So you have expectation of x times x minus 1 is equals to n times n minus 1 p square. Perfect. So you can write it as n square p square minus np square. Okay, so now this is the value of expectation x times x minus 1. What would be the value of expectation x square? Expectation of x square is expectation of x times x minus 1 plus e of x. We know what e of x is. E of x is n of p. N times p. So e of x square becomes n square p square minus np square plus np. So now we have the value of expectation of x square, and it's time to put this value in the formula of variance and find the value of the variance. So variance of x is e of x square minus e of x whole square. We know that the value of ex square is n square p square minus np square plus np, and expectation of x is np, but we are taking square of expectation of x, so we will have n square p square. If you cancel out n square p square, you will be left with np minus np square. If you factor out np from here, you will have np times 1 minus p. Therefore, the variance of a binomial random variable is number of trials n times the probability of success p times the probability of failure 1 minus p. And this is how we find the variance of a binomial random variable. Now it's a practice question for you all to find the standard deviation of a binomial random variable. Standard deviation of a random variable is equals to the square root of the variance. And I'm sure you'll be able to find it. And that's all for binomial random variable.